IUT. My name is Ross Franklin, and I will be presenting my submittal for the reverse engineering project. My product is the Bruz Buzz by Bruz Corp, which is me and my team. So our first step was to identify our competition, which was the Piggy flashlights. We went on popular sites like Amazon to find the reviews, and we saw all the reviews were pretty bad. Like, it broke really quickly. It only had a few colors, and the light wouldn't stay on that long. So we identified those as our needs to fix with our own flashlight. So next we did an action function table, which identified the actions that our flashlight would have to do with the functions. Then we asked the question about what would have to happen. So for the action locate the flashlight, we would use our eyes. But then for the question, we have to ask, can the flashlight be easily found? Like, is it bright colors, or is it big enough to be found with the eye? Then to crank the flashlight, it has to transmit the energy to the battery efficiently, and you have to think about the crank handle to allow for easier turning, so you can maximize the amount of energy for the flashlight. And then for turning the flashlight on, it must have a working switch and it must have battery. So we thought, is there always a large enough battery to keep the flashlight charged? Okay, then next, me and my group did a predictive sketch. For my sketch, I predicted that there would be a lever to turn some gears, which would turn a motor which charged the battery, and it would output it to two lights at the end, and there's a switch to the light switch, and there is a blocking mechanism down at the bottom. Now for the actual flashlight, I was somewhat close with the lever, but for the actual flashlight there's only one gear, and there were many more axles, and then for the lever it used a spring, which I did not identify in mine. Then for converting the mechanical energy to electrical energy, it used a dynamo, which I thought it was going to be a motor. And then it has two lenses and three batteries which were charged by the dynamo. Then our next step was interpreting these statements from our customers. Our entire class was each given a role where we were told to fill out a personality for. Then we each interviewed each other and asked each other about design and appearance, durability, multi-use, colors, noise, brightness, cost, ease of transportation, and strong battery. So after that, we compiled a list of frequencies and importance. We asked each person to rank it from 1 to 3, and if they got a 3, we added 3 to importance, and frequency is just the amount of times we got it. So the most frequent one was design and appearance, which appeared 66 times with an importance of 137. Next was durability with a frequency of 31 and an importance of 63, with multi-use at third with a frequency of 20 and an importance of 42. Then colors, noise, and brightness were about the same, with around 26 to 23 and 38 to 4. Then ease of transportation appeared quite a bit at 42 with an importance of 63, and a strong battery appeared 16 times with an importance of 38. Next, we used benchmarking data where we did several tests for each one of those categories. So for multi-use, we asked people on a scale of 1 to 10 for how effective it was at serving at multiple functions. The flashlight scored a 7, which is about average for multi-use. Then for design appeal, we asked them to rank it out of 5. So the flashlight got a 4.5 out of 5, which was really strong for our flashlight, but there was still room for improvement. Then compactness, we asked them to rate its size, how easily it was to be carried. That one got around a 5 out of 10. Then portability, it was very portable, but if we added a clip or strap, it would have been a lot better. Renewable energy, the battery runtimes were quite superior to solar, and quicker recharging from the sun would yield its more renewable effectiveness. The noise was quite loud. It was 78.3 to 80.4 decibels, which is way over the acceptable thresholds. So additional sound dampening material can reduce the overall sound. And finally, brightness. The flashlight was extremely bright at close ranges, but as you moved away, the light would get dimmer. So we decided to add brighter lights in order to enhance the brightness. Next, we did mind map, where we put all our ideas to paper, and we surrounded a central idea with each one of our own ideas. So we had must have strong battery, the battery would be charged by solar power and rechargeable, and a nice design. Next, we did C-Sketch, where each one of the group each drew 2 pictures, then we each added to each design. So we can see evidence of the original Piggy design here with upgraded batteries. Then down here we have what eventually became our design with the glove design, with a big battery and flashlights on the ends of the finger. When we got to the future, we ranked each idea against each other. Idea 2 was the original one, and concept 3 was the flashlight we ended up going with. So 0 is basically the baseline. Then if it got a 1, it means it was better in that area. And if it got a -1, that means it was worse in that area. So our idea ended with a score of 3 compared to 1 and 0. So then this is our main technical drawings. You can see the flashlights on each of the knuckles with a knife at the end of the thumb. You can have the dive watch there at the end with the screen. Then here are all the components and the side view. Alright, the science behind it. The lighting, we chose LEDs for battery efficiency and a mixture of white and blue light to account for the refraction of the water, since this is supposed to be a dive watch. For batteries, we chose a lithium polymer battery for its high energy density, and we would have coated it in epoxy for waterproofness. Then microcontrollers and waterproof wiring to keep the battery life for a long time. Then waterproofing, for the fabric of the glove, we chose a neoprene coated fabric for its flexibility, and we combined it with Kevlar for strength. Then all of the components are coated in tempered glass or steel to withstand high pressures. The knife is made of stainless steel to prevent corrosion, because you don't want your knife to be stuck in place while you're down underwater. And it has a spring to launch the knife out and a locking mechanism. Then the dive computers have a thermometer and a depth tracker to track how deep you are underwater and how cold it is underwater. Then it's all made to ISO 6425 standards, which ensure the electronics will function at that depth. So Q&A, this basically goes over what everything else in the slideshow. A quick synopsis would be, it's a glove with LEDs on the knuckles to provide ample light for underwater, and it's there's a knife on the thumb in case you get stuck underwater in anything, and it has a dive computer to calculate how much air you have left. Our design is better because it's cheaper to produce, and it has a lot more uses than other devices because it can also be used above land. Then how is it manufactured? It's manufactured using a waterproof, corrosion-resistant materials with LED modules on the knuckles, which are put on the light at the end of manufacturing. The dive watch and battery are secured using reinforced stitching and adhesives, and it goes through rigorous testing to make sure it adheres to the ISO 6425 standards. And then we've already gone over how it works. So that's all. Thank you for watching.